remove the new one? Well, if there's not possible, so it's not possible, I'm fine. Just fit to page and fit to the width and
Sorry.
no,
Okay, it's better actually, right?
no, there's it's missing some.
Really?
Yeah, yeah,
Sorry.
yeah. Can
Okay,
be
now
like
it's
this.
perfect.
Yeah.
Okay, fine.
Okay. Hello. So my name is Mathias Mantelli. I'm PhD student at Federal University of Rio Grande do Sul from Brazil. I'm going to present my master degree work called Vision-Based UAV Localization System using satellite images. So, yeah, uh, UAVs are being used in different tasks such as agriculture or delivering objects or even patrolling. And how do they localize themselves? Well, there are different models, of course, but most of them relies only in GPS to localize or estimate their positions. Some other models also use MU or compass, but some models just are based on in GPS. And GPS, as any other sensor, has some problems, such as or limitations, like it requires a minimal amount of satellites to provide a reliable position estimation. It also requires good weather conditions and no obstacles between the sensor and the satellites. And also there is this jammer gun that jammed the signal and then interfered the UAV position estimation. And as you can conclude, it's really bad for autonomous UAVs that are performing autonomous tasks. So how can we solve this problem? Like, how can we provide a solution for this problem UAV sensor? Well, a possible solution is many different UAV models are commercialized with an embedded camera, right? RGB camera, a standard one. And also, we can find satellite images on different softwares, and many of them are free, so you can go there and get images with a good resolution. And the question is it possible to, yeah, it's not good here. Yeah, that's better. Is it possible to localize a UAV image in a satellite image map? So this was the question. And actually, yes, it's possible. And this was our approach. So we have the drone. We point its camera looking downward. And then we get an image. We capture the image. And we had the satellite image that we use as a map. So what we did was, yep. We tried to localize and estimate where this image was in this map. So we compared the image of the drone UAV image with different patches of this satellite map. And for that we used a novel descriptor called AB brief that is based on brief. And we also use a particle filter to estimate the position. Our results, well, we had the highest average error. However, when you compare our map size, is right bigger than others, and our search space is really high. So when you see our error, its impact is lower than the other works. And also, we are performing a global localization, which means that we don't have any idea about where the drone was when it starts moving. So it increases the error, as we see here. So this is just one graph from our research. we compared one trajectory of the drone with 5 different maps, and here you can see the year of each map. And our data was captured on 2016, so we use one map that was 6 years apart from the data set, and we still could localize the drone. So, which means that we don't need to have a really updated map to estimate the UAV position. And as I said, global localization, we have at the beginning, we have a high error, but as the drone keeps moving, the error decreases, and even when the drone was over a homogeneous area, we still could decrease the error and keeps the drone localized. I have a video here. You can see it working. So at the beginning, the particles are spread over the whole map because we don't know where the drone is, so we need to test everything. And as the drone moves, here is the UAV image. We can estimate the UAV position. So the particles are converged. We call it convergence when it's good. And we keep it as it is. So the error is quite low. And we could localize in 4 degrees of freedom. And that's it. So if you have any questions, please let me know, or you can also read our paper. And that's it. Thank you for your attention.
Thank you, Mathias. Are there any questions?
Yep. Just curious, did you ever test it like, well, I'm not sure if, where are you at again? Or where,
Sorry?
where are you at? Do you have snow?
Brazil?
Okay. I'm just curious, like, I was thinking, I'm from Alaska, so we have lots of snow. So I was thinking snow would
Yeah.
probably affect that quite a bit, wouldn't it?
Actually, yeah, this is one of our problems right there. The snow and green areas like forest, we call these as homogeneous areas because it's always one color, and it's difficult to estimate the position there because it's all the places equal to other places. And we have a feature work that's are being developed right now to improve this, to correct this disadvantage that we are using a different camera to try to overcome this problem. But yeah, we comment it in our paper. There is a problem where it's a homogeneous area. We can't estimate the position. So the problem is this one. Whoa. Yeah. This is the problem. But when the drone moves out to these areas, we still can reduce the error and keeps it really low.
Okay, thank you, Mathias.
Thank you.
Everybody, please, thank you again. And let us welcome Giuseppe, who will tell us something about energy tanks for multi-robot interconnections.
Can you hear me? Hi, I am Giuseppe from the University of Modena and Reggio Emilia, and I will talk about our work on the stability of the interconnection of multiple systems. It is a control paper, so it is full of math. Even this presentation is full of math, but I will make it conceptual, so all the math you see, you can consider it as a fancy drawing or the background of the presentation. So, to start, I have to introduce you to the word of passivity because it will useful in the next slides. In the passivity world is all about energy flowing. So a system in this world can be seen as an element which can store energy and exchange it with the external world through its power port, which is namely inputs and outputs. A system is a passive system. A system is said to be passive if the variation of its internal energy is lower or equal the energy that flows through its port. What does it mean? It means that a system is passive if it receives some energy and it cannot store more than the energy it receives, and vice versa, it cannot give to the external world more energy than the energy it has. So usually what happens is that a passive system receives some energy and stores a part of it and dissipates another part of it. Why passivity? Because passivity is an elegant way to imply stability, and it's the easy way of implying stability, and as the wonderful property that interconnecting with a power-preserving interconnection to passive system results in a new passive system that, again, implies stability. So we asked ourselves, what if we drop the constraint about the power-preserving interconnection? So what if I want to interconnect my systems with a generic interconnection, whatever I want to do? Is that possible? Yes, it is. But so the problem is this one. I have n different systems, passive, all of them, and I want to implement a desired interconnection, which can be, for example, formation control. Okay, so the input of the systems, of all the systems, depends on the state of the other systems. And I want to implement this interconnection, and I want to make the overall system passive, so stable. Before illustrating our solution, I have to introduce another passive element, which is the energy tank. What is an energy tank? It's an element that you attach to your system, and it can store the energy that the system dissipates. So this energy is not wasted, but is kind of recycled in order to use it later when it needs. We proposed a modified version of this energy tank, which is called modulated multiport tank, or MMT. And this tank can be attached to multiple systems and can force the input of each system differently by the parameter alpha. So why it is useful? Because we can use that alpha to implement the interconnection we want to. So the interconnection. Disregarding the kind of interconnection, the actual interconnection we want to implement, it can be just one of three cases. It can be power preserving, that means that the energy flowing inside the interconnection is the same energy that flows out. So I have no dissipation or generation of energy inside the interconnection. It can be dissipative if the energy that flows in is greater than the energy that flows out. So the interconnection is dissipating, is wasting some energy. Or it can be generative. This is the worst case because the creation of energy is a non-passive behavior and it may lead to instability. And so we have to manage this case in particular. What we did, in the case of passive interconnection, namely power preserving or dissipative, we do nothing. We can manage it with standard passivity. But if the interconnection is generative, instead of create energy, we can take the energy from the tank and use it to apply the generative input to the systems. What happens if we have no enough energy in the tank? In that case, we have to slightly modify the desired interconnection in order to refill the tank with the damping factor beta. So, with this method, we could we proved in the paper that the overall system is passive, disregarding the interconnection we want to apply. And if this interconnection is passive, we can apply it forever as it is. If it is not passive, we can apply as it is until we have enough energy. So we applied this method to a multi-robot case. So we have n robots, and each pair of robots is interconnected with a modulated multiport tank that we use for implementing the desired interconnection. After some math, we designed the matrix A, which is the general interconnection of the system, and result in this model, which is a Porte-Hamiltonian model, which can be proved to be always passive. So here should be a video which will not start for sure. Yep. Okay, in the video that should be here, we have simulated some drones doing a formation control, and we applied a non-passive interconnection, which is each couple of drones is connected with a spring, and we instantaneously change the rest length of the spring in order to change the formation. That's not passive because we are injecting energy to the system, and with this system, even with other obstacles into the environment, the system keep being stable. And that's all. Thank you.
Thank you, Giuseppe. Are there any questions? If okay, there is one.
So yes, thank you for the presentation. How do you said that you also have obstacles in the in the simulation? How do you consider obstacles then?
We consider the obstacle as a repulsive potential field. So
Okay.
the input of each drone consider the interconnection force and the force, the repulsive force from the obstacles.
Okay, thank you.
Thank you.
Any other questions? If so, thank you again. And let's welcome Fabian, who will tell us something about learning vision-based flight in drone swarms by imitation.
Cool. Thank you. Hello, everyone. So my name is Fabian, and I will talk to you today about my work on imitation learning and how we can use imitation learning to synthesize flocking behavior. Oopsie, that went by itself. So I'm going to start with a short video, an excerpt from a video, where we see a couple of starlings, actually 1,000, that are flocking together. And it turns out that these birds, they pay attention to roughly 7 birds, at least that's what the data shows. And this can change throughout the flock. And the behavior is mostly dominated by visual perception. At least this is what some researchers say. And we can, if we model it mathematically, we can use 3 rules that are known to, I think, everybody by the middle of this week, which is cohesion. So they stay together, and they align their heading direction, and they also separate, as you can see here in the video. So if we look now into the state-of-the-art of swarm deployment, then we have one example, which is centralized control. And here we have very nice work from UPenn, where you see a swarm of quads that are taking off, and they're completely controlled by visual odometry, so visual inertial odometry. So they're not using any GPS information, no motion capture system, and they can go through several formations and through that with such little drift that they can actually land again on the same spot. But the problem is here that it's a single computer in the background. Why is this just going? Okay. There's a single computer in the background that controls all of them. So of course this introduces a single point of failure, and that's what we do not want in our swarm systems. So the next example is sharing of positions. So in among us here, we have a researcher named Gabor, and he's responsible for this work. So it's a very nice example of 30 quads that are taking off and flocking with the bio-inspired algorithm that is optimized with an evolutionary algorithm. And what's really nice is that it's bio-inspired, but not to the degree where they're actually using visual perception to localize the other agents. And the third big group that's often used is visual markers. So you do use visual perception, so in that sense you're decentralizing. For example, with spherical markers, or you have blinking LEDs, or the system from this group called Vicon, which gives you very accurate and fast predictions of relative position. And also the newest system, which is also from this group here, which uses ultraviolet spectrum to detect range and bearing to other vehicles. So, of course, if you look at the video before of the swarm in biological swarm, then you see, okay, they're not really controlled by a central entity, they're also not using Wi-Fi communication, and they don't have markers attached. So there must be a different mechanism that they use to remain collision-free and also together in a flock. So what we're doing is direct visual imitation. So we can synthesize the behavior by flocking algorithms, and we can also mount cameras on these agents and then let them flock and learn from their behavior. So that's exactly what we did. And I will show you now, oh, actually, yeah. I will show you now the work that was actually accepted on Monday this week, so it's very fresh. And yeah, show you how it's done in our system. So here we have 3 agents that are taking off. This is in the gazebo simulator. And they're acting to 3 rules. One is separation, the other cohesion, as you've heard many times. And also optionally, you can give a migration point to this group. But for our case, this we only use separation and cohesion as the labels for our imitation learning algorithm. So now you can see that the drones are taking off in a takeoff zone, randomly assigned positions, and they're migrating to the other point that's on the other side of the arena. And now we're going to look at what one agent perceives. So we mounted cameras in a cube map configuration, so you have omnidirectional visual inputs. And so now we actually replace the flocking algorithm by a convolutional neural net that takes these images as inputs and produces 3D velocity commands that match the targets that we defined. Okay. So training looks as follows. So we take off again, and now we sample 3 trajectories from the expert, which is the flocking algorithm. And in the next iterations, we use a technique called dataset aggregation. And you can see every single iteration, a neural network learns a bit more what flocking actually looks like. So in the beginning, the distances between the agents, they're kind of random, and they don't really know how to flock yet. But over time, and even after 30 iterations, they take these visual inputs, they find the important features for flocking, and they converge to the equilibrium distance that you would find with the flocking algorithm. And at the end, you can actually learn this behavior. But what this leaves open is, of course, you do it in simulation, or we trained this in simulation. So we have a shift between reality and and simulation. So what we did is we flew around our motion tracking hall and collected images and put them as backgrounds for those drones. And now it turns out that we can use this with some data augmentation also we can retrain this network and then flock inside the motion tracking hall. So here's the leader-follower experiment. The follower is completely vision-based, but it's not really able yet to perform this flocking behavior because it drifts off, for instance, or it loses track of the other agent. But in general, the general flocking behavior already is there. Right, so we do another 3 iterations in reality, and then I'll show you the results of that. So again, the follower is vision-based, and as you can see here, it can actually follow the other agent just based on monocular vision in our motion tracking hall. And the agents receive their own positions, but they're unaware of the other agent's position, and they can keep the equilibrium distance. They make minor mistakes, but yeah, in general, they learn the behavior. Right, thank you for your attention. This work was performed with the 3 gentlemen in the top left corner. And also, I wanted to do a quick ad for our IROS workshop. So if you want to come join us at IROS for Aerial Swarms workshop, we extended the deadline, of course, and we expect nice contributions from you. And you can also see I indicated there's some familiar faces at the workshop. Thank you very much.
Thank you, Fabian. Do you hear me? Yeah. This was very impressive. Are there any questions?
Hi Fabian, it's a really nice work. So what I wanted to ask is how do you plan to extend this framework? Because I'm sure you're aware of limitations and also, let's say, limited settings, because in your demonstrations you were basically drones were flying within one plane, so there was no even, right? Am I right or I'm wrong?
So that's why I
I'm not about flocking, about real demonstrations, or maybe I missed it.
So here you actually have that case where one drone is performing a carousel, I called it, and you can see that the leading agent is actually performing a Z sinusoid, and the other agent, it's not completely perfect, of course, because it's all based on very small images, but it can actually follow these the Z altitude quite well.
Okay, thank you. And then, I think within the simulation you could use, this state exploration that also when you like lose the leader, then your network may like learn to continue within last frames, right?
So I'm not sure
I mean, do you use this technique of state exploration? Because in simulation you may also embed some, intended fluctuations or maybe some.
No, it's so this is actually the most crucial part of this whole work, because if you just follow the expert policy, let's say you follow the flocking algorithm, you will never be able to learn this behavior reliably. So you need to, and this is what dataset aggregation, or DAGger, does. It keeps following an untrained policy, so you can make mistakes, and you can correct your own mistakes by following your own suboptimal policy, and you collect data from all of your failure cases, and at the end you will learn the behavior because you've learned to correct all of your mistakes. That's
Okay, thank you.
Thank you. Please, next question will be during the banquet.
Yeah.
If we may share the papers, meet at the workshop. We'll definitely see each other there.
Thanks a lot.
And please welcome Enrica, who will tell us something about drone swarming with limited visual sensing.
Thank you. Hello, everybody. I'm Enrica Soria from the EPFL. I'm currently pursuing my PhD under the supervision of Professor Dario Floreano at the Laboratory of Intelligent Systems. And today I would like to present you my research about a predictive approach to drone swarming. So instead of defining again for the 1 million time what swarming is, I'll go through the motivation. First of all, most of the state-of-the-art swarming algorithm use only the current state of the system to compute the next control inputs of the agents, and what my question was is, can we actually improve the reactivity and the synchronization of the swarm, also introducing this concept of prediction? And can we at the same time guarantee safe flight for the agents? And my hypothesis is yes, through prediction, and it is based on the observation that animals in nature may interact with the future prediction of the world to improve their synchronization. For example, let's think about a school of fish. They are able to suddenly change their direction at all of a sudden, and they are doing that all together at the same time, and they cannot certainly do that just basing on the current state of the system without considering any model behind. So in the next slide, I will perform a comparison of a state-of-the-art swarming algorithm with my predictive approach, and for this I'll introduce the model that Gabor already introduced on Monday, and therefore I will refer to this in the next few slides as a potential field-based algorithm, because all the rules can also be interpreted as virtual forces applied to every agent. And these forces are repulsion, self-repulsion, friction, and obstacle avoidance to deal with convex obstacles. And here's the model. I won't go through the formulas, just want to highlight the fact that this model bases on the positions and velocities of the current time step of the other agents and some shield agents, which are virtual agents introduced in order to avoid obstacles. And I will compare this with the MPC formulation, which uses similar rules introduced in the cost function, which are designed to drive the distances and the velocity to preferred values. And to this, I'll add the knowledge of a model, so the knowledge of the quadcopter dynamics plus a collision avoidance constraint, both for agent-agent avoidance and agent obstacle avoidance. And finally, we will solve an optimization problem where we try to minimize this cost under these constraints, and the output is the control commands for every drone at the current time step. So, sorry, in a future window of time steps, but we are just applying the first one, because at every time step we repeat the optimization. Yeah, so here we have the results. On the left you can see the trajectory followed by the swarms. Just to let you know, I just used only 3 drones for now because of the computational cost of the predictive approach, but I plan to overcome this limitation in the next weeks. And we can see that the swarms start from the bottom up to the top, and then what we see, actually I don't know if the video is playing or not right now, but the predictive approach, with the predictive approach, the swarm reach the end point much quicker. And sorry, I don't know why you have 2 start points, but I was saying the green one is the start point and the last one is the end point, as you have seen in the videos. And so let's analyze also the distance and speed. I didn't mention that, but to the Vasarely algorithm, I also added a cohesion term in order to have a fair comparison. Otherwise, in some cases, the agents could have diverged from one another. And what we see is that not only the predictive approach reduces the time to cross the obstacle field, but also the values of distance and speed are much closer to the reference values, and the variance is reduced. So to conclude, we have seen that a predictive approach to swarming improves reactivity and the agents cross the obstacle field faster. The preferred distance and speed are tracked better actually, but a very heavy downside is the fact that computational cost and time increase and interpretability also decrease. And as a future work, therefore, I'll try to improve this computational time, deal with changing topologies, because across a long time, the neighbors of a single agent can vary, And this can be a problem with the predictive approach because we are performing some numerical differentiation. Therefore, we have to know which measurement is associated to the previous measurement. And I'll also implement the decentralized version. For now, everything is computed in simulation on a single PC. The goal will be to have the swarming running in real time on different drones. And yes, finally the deployment in real world, as I mentioned. So thank you for your attention, and again, join us at the workshop. Thank you.
Thank you, Enrica, for the quick presentation. Are there any quick questions? The question was how long your prediction horizon is.
So the horizon is 2 seconds. Yeah. Actually, yes. Let's say that the parameters were tuned for these special scenarios. And what I'm measuring for tuning them is collisions, connectivity, and so safety, connectivity, union of the swarm, and the distance to the preferred values.
Thank you again. And please welcome Charlie, who will tell us something about planning under temporal uncertainty and varying congestion levels in multi-robot systems.
Which one's the laser on this? Laser? Laser is in the middle. Echo. No, I can get it so it's like, can I only chance to get the PDF so it's like one slide per page, just 'cause I've got a load of animations and it'll screw it up otherwise. Oh, it's screwed up? Why is it screwed up? Oof. Oh, fit the page. Oh, no, it's okay. Now it works. Cool. So, hi everyone. My name's Charlie. I'm from the Oxford Robotics Institute at the University of Oxford, and I'm going to talk about congestion-aware planning for multi-robot systems. So, throughout this presentation, I'm going to base myself around the multi-agent pathfinding sort of setup. So we've got a number of agents who want to get to their respective goals as quickly as possible. And the main idea we're looking at is that if we have multiple robots in the same part of the world at the same time, we're going to get an increase in uncertainty over action execution. And therefore, the more robots we have, the more uncertainty we get. So for example, if we were to look at this warehouse map here, and we had 2 robots coming along on one edge, if that edge was narrow enough, we could end up with 2 robots coming together, and then one having to back off to let the other one through. And that brings in a load of temporal uncertainty. So there are generally 2 approaches and 2 extremes to dealing with this. One is the multi-agent pathfinding solution, where we just completely block out agents from visiting the same part of the world at the same time. And the other approach is done in continuous motion planning, where we just deal with these interactions at execution time via collision avoidance. But what we want to ask is, can we be in the middle? Can we deal with these execution time interactions at planning time? So what I'm going to start with is by talking about sort of a discrete version of the core of our framework in the form of reservation table-based planning. So we have this central reservation table here, it's global, and we have our 2 robots, Betty in the blue and Barney in the yellow, and each one wants to get to their colored stars. So we have a planning order here. So we start with it being Betty's time to plan, and Betty doesn't think there's any robots in the world, so Betty just goes straight to its blue star. Once Betty has, there we go. Okay, cool. And then Betty has its plan, and it inserts it into this reservation table. So we can see it's inserted in a discrete form here. So now Betty has planned, we move on to Barney. Now, Barney knows there is something in this reservation table. And so first what Barney does is he examines the reservation table and sees that actually, if he was to move to the right here, straight away, he's going to collide with Betty, which we don't want. So what the solution to this is for Barney to, if this is going to work, which I don't think it is, There we go. So the solution for this is for Barney to wait and then follow its shortest path to get to the goal. So then Barney will insert into the reservation table. Thank you. We'll insert its path into the reservation table. So we now have both paths in here. So any future robots who want to plan can see what's been inserted. And now we can execute the plans. And we see that they both get to their goals safely. So this was the discrete world. But we want to work in the world of continuous time. So the first question we have to ask in this is, how do we model action durations? Our solution is by probability distributions. So over the duration of how long it takes a robot to carry out some action, in this case, navigating somewhere. So this is for when we have 0 robots in a part of the world. But what happens when we increase that number of robots? Well, for 1 robot, for 2 robots, and for 3 robots, what we see is that this distribution shifts to the right because the robots are going to slow each other down. And the distribution also widens because we have a higher uncertainty over this execution. So from this, the next question we have to ask ourselves is, firstly, we just show this is actually a reasonable thing to do. We have actually gained data from simulation to show that these sort of relationships actually hold in practice. So the second question to ask ourselves is, what edge is a robot most likely on at a particular point in time? So we're going to go back to our friend Betty here, and this time Betty is on a simplified map, just a straight line, and Betty wants to get to its star again. Now, the simplest path for Betty here is just to go straight through. And because there's no other robots in the world, Betty will act according to these sort of very sharp distributions here. So each with an expected duration of about 1.26. So now we can ask, at different time steps, what edge is Betty most likely to be on? So at time 1, Betty's most likely to be on edge 1 in this graph here. At time 2, edge 2. At time 3, edge 3. And at time 4, it's most likely to have finished. And given these distributions, this makes sense. But now what if we add Barney back into the mix? And Barney wants to follow 2 edges Betty wants to follow, but then goes off to a different goal. So Betty has no choice. Betty's got to follow the same path as before. But because of Barney's presence, it means that we are now going to end up with long distributions on these first 2 edges. So we've now have expected duration of 2.55. So if we look back at these graphs that we had last time, we can see in the orange, after Barney arrives, at time 1, we're now very, very likely to be on edge 1. At time 2, still edge 1. At time 3, edge 2. And at time 4, also edge 2. So we can see how this has made it a lot more difficult for Betty to get to its goal. So what we do is we take all this modeling and we form a new structure called a probabilistic reservation table. And the question is to ask, what can we do with this? So we have a planning order again for each of our robots. So for the first robot that plans, this reservation table will be empty. So we can form a very simple Markov decision process of the environment. We can then solve it using some sort of heuristic search method to get a policy. With this policy, we can get route information for the robot and insert it into the probabilistic reservation table. Then for our second agent who plans, we can take the information currently in the reservation table to summarize the team behavior of the robots who have already planned, then form a new Markov decision process for that agent, solve it to get a policy, insert the route into the table, summarize the team behavior again, and so on and so forth. Now, in our research group, we care about probabilistic guarantees over robot behavior. So, for example, what's the probability that a robot gets to its goal within 10 minutes? And so what we can do in this framework is take information from the policy, take information of our distributions from this reservation table, and build a new model. And this new model, we can use formal verification techniques to obtain the guarantees we want. So, I'm currently in the process of experimenting on this framework. So far, all I've got is scalability results, but we've found that on various maps of various different sizes, we're able to scale nicely up to 15 robots I've tried with, which for MDP-based solution methods with formal guarantees, this sort of relationship on the graph is really great because it's sub-exponential. Soon I'll be carrying out simulation experiments, then hopefully some experiments on real robots, And then if I'm lucky at some point soon, I might have the opportunity to deploy this work on a set of agriculture robots. So, thank you for listening, and if anyone has any questions, not now, just feel free to come and chat to me at some point. Thank you.
Thank you as well. Are there any questions? We are recording this, so we should speak to the microphones.
Thank you. Thank you for the presentation. I'm wondering, did you consider the dynamic or kinematic constraints of the robots? So it's a first order kinematic constraint, or?
In short, no, because what the aim of our research group, we're very much high-level mission planning. So we assume the existence of for example, the lower-level motion planner to deal with all the things like the robots avoiding each other in practice and their movement. And then what we want to do is reason over that. So we just assume that stuff at a lower level, and then it's sort of almost in a hierarchical way. We just look at the high level. That's all we care about. And then hopefully through these models, we can actually then reason about it accurately, and then those guarantees we get later on will also be accurate.
Okay, thanks.
Any other questions?
Okay, thank you. And you said you plan sequentially for the end robot you have. Do you have a sorting method for creating a list of the robots? Like you sort the order of the planning robots according to some prioritization or something?
So obviously I'm very aware that and there's been a lot of work looking at the fact that the planning order of the robots can really affect how this works. In my work, I'm basically just assuming, I basically have robot IDs, and I just assume that the robots are planned according to their ID. It would be an interesting piece. So in the future, what we want to look at is we have mechanisms within this framework to know how inaccurate a robot's model was when it planned, for example. And so this might be an indication for replanning in the future, so we can get more and more accurate plans across the team. What might be interesting then is to use these indications as an indication to maybe swap robots around in the plan. So the robots that are being essentially really screwed over by other robots getting in its way, if we put that higher up in the planning order, then we might be able to give that robot priority through it. So at the moment we don't have anything for that, but in the future there's definitely room to be able to do something more interesting with that.
Okay, thank you.
Thank you again. And please welcome Michiel, who will tell us something about the Valley of Death for robots.
So I will tell something about my department, Intelligent Autonomous Systems, at an organization called TNO. I'm actually quite new to the field of robotics. So this presentation will be, I think, a bit different than most of you who are doing a PhD in the field of robotics. So a little bit about me. My background is mechanical engineering, process and energy technology. After that, I started working at this organization, TNO, where I did a traineeship. And within the traineeship, you have three spots of 8 months. You work at a different department. So my second department was at Intelligent Autonomous Systems, where I actually got the first taste of programming and autonomous systems. And I really liked it, so since 7 months I worked there full-time at this department. So TNO is the largest RTO, research and technology organization in the Netherlands. And what the purpose is of this organization is to bridge the Valley of Death, which is the bridge between what is being researched, or a bit generalized, what is being researched in academia and what is actually implementable in industry. So there's a gap there, and RTOs in general are there to help bridge this gap. So key thing of RTOs is to collaborate with both academia and industry. Well, within our organization there are 9 units. I work for the defense unit. So our biggest customer of the department is actually the Dutch Defense Organization. But we also work for instance, smart industry and robotic companies. What we do in a bit generalized, we do system engineering, we do artificial intelligence, we do sensor systems, heterogeneous sensor systems mainly, and we fulfill an integrator role between academia and industry. I'll skip this. So we do that, I'll set it briefly in 3 portfolios, and then I have some examples of what I currently do. I work in multiple projects, so I'll show a few of them. So we work in 3 portfolios, so that stresses, that shows the different customers we work for. Manning and automation is mainly the defense organization. Situational awareness is to build up your vision of the world surrounding you using heterogeneous sensor systems and unmanned UXVs. Unmanned vehicles can be underwater vehicles, drones, aerial vehicles, or ground vehicles. And smart industry is a small portion, but I really like it because my background is in energy. A small portion is for the energy industry. So one project that is starting right now, and I'm really looking forward to it, is we built we call it an intelligent machine that can help you, or can help the Dutch defense organization for target selection and scheduling of tasks. We build algorithms and models to simulate a mission, and a mission consists of goals. So these kind of projects we do here, where we build this intelligent machine, we actually build some kind of a demonstrator to help the Dutch Defense Organization think about how autonomy and autonomous systems can influence their operations. To do that, we build this demonstrator. It's a software tool which simulates autonomy. But meanwhile in the project, because this is of course, this is the technical aspect, and it's very, very challenging to reason about a complex world, a defense world where not a lot of data is available. That's very challenging for us scientists to think about how to solve this problem. But next to that, there's within these projects also people thinking about, okay, how to think about utility in the defense domain. We use a utility-based reasoning in this framework. We think about, okay, how should the human-machine interface look like? And a big part of this is always ethics. How can, like, what can you do with autonomous systems in a defense organization? And I actually really like that because it makes the project really multidisciplinary. We do a big part of the technical stuff and the implementation, but other departments help to think about, for instance, how to formulate you have a mission and how to formulate that into a utility function. Other projects in the field of situational awareness. I don't know how much time I still have, but okay. Really quick, 2 examples is in one we develop a system of a sensor system. The sensors are not of our organization, but of other organizations. But we do the pre-detection sensor fusion, and this the purpose of this sensor system is to detect bombs, IEDs, next to the road. And in the Alpha project, there's actually a really fancy movie there, which is too fancy. I think it's so funny. We develop an anti-drug smuggling. This doesn't work. So this is like a teaser for a documentary that will come out this September, I believe, that is more on the details of this project. But it is an anti-drug smuggling system for detecting low flying and slow flying aircrafts near the southern European border to detect drug smuggling from Africa. Yeah. So what is next for our organization? We do a bunch of stuff. The projects I show here are close to implementation by industry or far away, like the one on transferring a mission into an autonomous smart system. So we have some steps to take to go from software demonstrators to complex simulation, for instance, ROS and Gazebo, hardware integration, and then system integration all the way on the right, that actually people start using the solutions we work on. And what I think is very important for an organization like us, and what I find very inspirational about the things you do, we are pretty spread out in what we do. Our work is more general. You really dive into the topics, deep into the topics, and I think therefore collaboration is the best way to realize impact and have your research end up in products eventually. Thank you.
Thank you, Michiel. Are there any questions? If so, thank you again. And let us welcome Hai, who will tell us about multi-robot collision avoidance in dynamic, uncertain environments.
This is the next slide. And this is the pointer. Okay. So, hi everyone. My name is Hai. I am a second-year PhD student from TU Delft in the Netherlands. I'm going to present our recent work in collision avoidance for multi-robot systems in dynamic and uncertain environment. So, as we all know, the multi-robot systems will be deployed for like this delivery or cinematography inspection in the future, and the local collision avoidance among the multi-robot systems will be a very important problem. So our first work is a robust local motion planner, which can generate collision-free motions for each robot in the systems to avoid collisions with other robots, as well as the dynamic moving obstacles. In this case, it's the persons. And in this work, we consider the humans, the persons, as moving ellipsoids, which we predict their future motions based on the constant velocity assumption. And we also consider the localization uncertainties and the motion disturbances of the robots. And we predict this uncertainty. Then for the future planning horizon at each time step, we formulate a chance constraint to guarantee that the collision probability between each robot with any other obstacle is smaller than a threshold. And we use some linearization techniques to make these chance constraints to be trackable for some general optimal control solver. And we also use the nonlinear model predictive control to plan this local motion. For planning for multiple robots, we use the sequential planning framework, which means after each robot plans its own trajectory, it broadcasts its future planned trajectory to any other robots in the team. And for any other robot, it plans its own local motion, avoiding all the future trajectories of other robots in the team. For more details about this work, you can read our paper in RAW. So here is a very simple demonstration of the collision avoidance. Yes. So the two drones are required to swap their positions while avoiding the moving person. And in this demonstration, for the localization and the perception of the person, we rely on the ObtTrack motion capture system. But to simulate the noise, we add a very large simulated Gaussian noise to the measurements. And today we are focused on our next work on multi-robot formation navigation in dynamic environments. In this work, we consider the robots navigating in formation in an environment consists of both static obstacles and the dynamic obstacles. We have achieved real-time distributed collision avoidance for the formation by splitting the formation to avoid the obstacles and merge them again after avoiding. So given a team of robots, for each robot, we consider its limited sensing ranges and the communication ranges. So first step is for each robot, it computes an obstacle-free region, which is represented by a polytope, so it's convex. Because each robot has a limited sensing range, so the obstacle convex region each robot computes will be different. So after each robot computes their own convex regions, they communicate their convex regions via network flooding. And so for each robot, after getting the convex region information of any other robot, it starts to construct a graph, which we call it the intersection graph. So in this graph, each vertex represents a robot, and each edge between any two vertices in the graph means the intersection of the convex regions between the two robots. For example, the edge EIJ means the intersection between the convex regions of PI and the PJ. And based on this information, the robot starts to make a decision, split or merge. So it's very intuitive that if the intersection of all the convex regions of the team is too small, like here is too small, that it cannot, that the formation is not be able to occupy this region because it's too small. So it will have to make a split decision. And the split decision, after the split action is computed by graph partition. Because we just constructed an intersection graph, and we perform a graph partition algorithm to partition this graph into several subgraphs. And after the partition, like in this case, the formation of the square formation of 4 robots are split into 2 subformations, subline formations. And then for each subformation, their intersection of the convex regions now are big enough to occupy the subformation. And for the merging decision is like this. So at each time step, all the subformation communicates their intersection of convex regions with any other subformation, and they compute the union, the intersection of the intersections of those formations to say if the final intersection is big enough to hold the big formation after merging. If it is, then they start to merge. So this is, all right. So all the future, the previous steps are to determine the future region for those formation. After getting those region information, then we perform a formation optimization algorithm, which can generate the target positions in the desired region of each robot in the formation. Then after getting this goal information, we then use a local motion controller, like the previous robust MPC, to drive each robot to their target position. So here is a short video. So the square formation avoids the person by splitting into two line subformation and merges back after avoiding. And here is a simulation of 16 robots. A team of 16 quadrotors avoids the static obstacles. So in conclusion, we have achieved local motion planning for a team of robots navigating information in the environments with static and dynamic obstacles. We consider the localization and the sensing uncertainties of each robot. And this algorithm is in real time. So for more details about the graph partition, about the communication among robots, you can read our new paper in ICRA, in this year's ICRA. Thanks.
Thank you, Hai. I'll have to ask you to leave the questions after the final talk, so we are in time for the banquet. And I would like to welcome Lyubomyr, who will tell us about robotics and autonomous systems group, which is probably called SoftServe.
Hi, my name is Lyubomyr and I'm from SoftServe. Did any of you heard of SoftServe? So great, you yes, some of my colleagues are over there, so they say that they did. So you have a chance. I will tell you about the company. And by the way, I want to say thank you that you are still here, not running to the banquet. And so at SoftServe, SoftServe is a global advanced technology IT consulting company with a headquarters is Austin, Texas, and we have offices in our 12 countries, including Britain and Germany, Poland, Bulgaria, Ukraine, and many others. And my department is focused on most advanced technologies like big data, AI, data science, IoT, XR, and others. And we are working with generally early majority and early adopters, but I guess that our robotics group will soon deal with also with others, since robotics is very emerging field. And we since robotics is done not only in industry but also in universities. We collaborate with many universities all over the world. Among them are ETH and University of Texas, Technion, and many others. Not all of them are enlisted on this slide. And we also some of my colleagues are co-authors of a couple of books which you can purchase, and we also have several decks of cards. One of them you can download for free from this website, and this is not a cards for a playing. These are cards for learning, because from them you can get in touch with most cutting-edge algorithm in big data, in data science, and in IoT, and not only to learn something, but there is already given comparison. So if you want to choose which algorithm would suit best for your course, you can just use those cards and select which one's better. So, and as a part of Advanced Technology Group, we took part in development of several projects, among which are smart parking. We, you know, one of the biggest problem, at least in Ukraine, is to find a parking place. We can circle around for 10 minutes to find a place. So we have a solution where I have one camera on top of one of a building. You detect the free parking places, and this big screen tells you where you can park. We also have Face ID, which helps to greet the customers when they come to conferences or meetups, and we use them also for entering our buildings. So our employees do not have to present any cards; they just present their face to a table, to some tablet, and they can enter. And this is one of our robots. We call it Booter, so it's multifunctional robot. It's a catering edition currently, so it serves cookies during meetups and conferences. And here are some services that we provide. Let's skip several slides. And yes, we are using Cross, and we're using digital twin concept, of which I believe you are all aware. When you have a real hard copy and a digital copy, you compare the behavior of both of them, and you can either tell if a robot is behaving not as you expected, or you can use it for predictive maintenance and for all kinds of reasons. So I guess I have not much time to show you the video, but you will have the slide, so you can just press this link and see the video of with the Booter. So it's multifunctional because you can easily remove the upper part, and you can place anything on top of it, and the platform will behave as usual. And we developed it entirely from scratch, so a mechanical part and frame and a PCB and all the software. And yeah, I guess you've seen lots of that. And another robot that we developed together with our XR team is a robot which is controlled from VR set, and it streams video to the glasses. And we adopted this algorithm to many similar types of robot, which can be used for inspection, exploration, and lots of many tasks. Here you can see the no, you can't, because it's PDF. So it had to be a slide where you could see a video from the headset. And another robot which helps our guests to find their way to our employees. So if someone comes and wants to find an employee but doesn't know where his working place is, the robot can easily help to find the way to the employee. If it is somewhere else, it will drive it. It will follow the way to the new place, like a meeting room or something else. And this is our outdoor platform, which can carry heavy luggage, but we are using it not only for like some cases like cleaning their parking place in the winter. We also using it for some scientific projects which we are working on together with several universities, like in Lviv in Ukraine, and in United Kingdom, Coventry University, and 2 universities in United States. And one of the goals of this project is to my PhD student explained the basic idea on Monday. So we develop a controller and observer for this project, and we wanted to take into account the dynamics of of the vehicle. And I guess you all are looking for some real-time controllers, and I guess we have a possible solution, because for this project we're using a fuzzy controller, which is very fast. You have to pre-compute some, you have to do some computations, but you are doing them offline. So really it's close to real time. And our state observer is also pretty fast, like a couple of milliseconds, one or two, depending on some conditions. So, and we also, as a company, we're also working with robotic arms for like cobots. And the last slide, yes, we are of course working with some giant robots, like an arm on a platform. And this is last slide. So we also taking part in preparation to M0 challenge together with FEE-CTU University. So I guess that's all for now. Thank you. And so if you are we have if you have some possible project in mind, we are always open to cooperation with universities or with industries. And you know, when there are presentations which are connected to robots, and if someone from industry is presenting, there is some very common phrase at the end of the presentation, which I'm going to use also: we are hiring. So, thank you.
Thank you, Lyubomyr. So if you have any questions, please ask Lyubomyr after we end this session. I have just a small note. Lyubomyr didn't stress enough the playing card games for machine learning. Look at that, it's awesome. Download it, buy it if it's possible to buy it. I can't stress that enough. And now Honza will tell us something about organizing the banquet.
All right, so please take off all of your belongings right now, because again we are leaving this room, and it's gonna be closed during the night. So right now there are guides waiting for you in front of the building E, so just get out of the building and there will be people splitting you into groups. So they will guide you to the nearest metro station, which is Karlovo náměstí, and they will take you to the brewery. And so if you have your tickets ready, or I posted, as you read in the Slack, there is the information about how to buy them through the app. So if you have it, that's great. If you don't have it, I think there will be option to buy it at the vending machine at the metro station. But I'm not sure if they are already made up for the credit card. So probably we'll have to have coins ready. So I think the app is much more convenient way than have some spare Czech crowns. So if you don't have it, you can do it right now. Yeah, it's on the Slack. I can actually find it on the website, so you know how it looks like, and it's in English. So don't worry, no worries about that. And it has to be, the only limitation, it has to be activated online. So please do it right now and buy the. Okay, great. I don't want to know that. So yeah. So there is like random ads about where you can use this app. So if you can download it and buy the 32 crown ticket to go to the pub, I cannot show it to you because. Jo, pejde.